Hello and welcome to module number 2 of 4.6 related rates. This module is going to focus on geometric shape problems. Now, if you recall from module number 1, every one of those word problems involved a right triangle of some kind, and therefore we use the Pythagorean theorem. This module is quite a bit different. It's going to give us a different shape every time, and the key idea now is it's not just one formula to know. You actually need to know all the different kinds of geometric formulas that could come up. So for two-dimensional shapes, area, circumference, and perimeter will be common quantities to know. And for three-dimensional solids, you'll be dealing with a lot of volume and surface area. Now imagine this. If a shape is changing size, if the area, for example, were to change, then you know that its radius or sides or height will also change with it. So in these related rate questions, we're going to be analyzing how the change in one quantity affects the change in another quantity. So let's take a look at all the different shapes that could come up, and here's a quick rundown of their geometric formulas. So let's start with the beloved square. For a square, you will need to know your basic formulas such as area equals side squared. Base times height is of course what we use for rectangles, but in the case of a square, the side lengths are the same. Now, here's the key to really understanding this module well. If you were to take the derivative of the entire formula, a equals s squared with respect to time, what would our derivative be? Well, just like before with implicit differentiation, the derivative of area, a, with respect to time is simply called dA dt, which is a rate variable, and that's going to be equal to s, the derivative of s squared is 2s, but don't forget, times ds dt, because of implicit differentiation, is what we have to remember to use. Now, what's another formula that could come up for a square? Well, how about perimeter? How do you find the perimeter of a square? It's just 4 times whatever your side length is. So once again, if I said take the derivative of this with respect to time, what would that look like? Well, derivative of perimeter would simply be dp dt equals, and the derivative of 4s is simply 4, but remember, times ds dt. So a square is actually fairly simple to use, and this will be a common type of question we'll be dealing with. Just remember how you take the derivative of each of those formulas. Now, let's go to the circle next. A circle is much like a square, except instead of a side length, you're given just simply a radius. Now, the area is not radius squared. It's multiplied by a factor of pi. So we know our formula, very famous formula for the area of a circle, is a equals pi r squared. What is the derivative of this equation with respect to time? Well, that would be dA dt equals, and what would pi r squared be? Well, pi is simply a constant, and we're going to use the power rule. So this would be 2 pi r, and then times dr dt. What about the perimeter of a circle? Well, we call that circumference, and that formula would be 2 pi r. So what is our derivative of circumference? Well, with respect to time, our derivative of this formula would simply be dc dt equals, and in this case, notice how the exponent of the radius is simply 1, so our derivative would be 2 pi, and then of course times dr dt. Alright, so circles and squares are actually quite similar because when it comes to their areas and perimeters, or areas and circumferences, it's pretty much the same formula. The change, of course, is circles involve pi, squares do not. Alright, let's continue to look at rectangles and triangles. And this is where things will get a little bit more interesting. Hello. Alright, with rectangles, notice how, in this case, you've got two different variables. In a square and circle, there was only one thing to keep track of. Now, this is what you'll want to make sure you know about. The area of a rectangle is very simple. It's length times width. But if I said take the derivative of this equation with respect to time, knowing that area, length, and width are 3 different variables, look at what we end up getting. The derivative of area is simply dA dt. But what would you need to use in order to take the derivative of L times W? Well, that would be the product rule. So what do we get? That would be first times the derivative of the second plus the second function times the derivative of the first. Do you notice how a rectangle is much more complicated than a square, because you could potentially have two different measurements affecting the area, whereas on a square there's only one value that would possibly change. Now what about for the perimeter of a rectangle? This one will actually be pretty darn easy. Perimeter of a rectangle is simply 2 times the length plus 2 times the width. So if I said take the derivative of that with respect to time, we won't need the product rule this time. Simply we'll get dp dt equals 2 times dl dt plus 2 times dw dt. So that one was simply just using each derivative individually. Not too much happens there, or nothing too complicated happens there. All right. So a triangle will be very, very similar. The one major difference, instead of length times width, we use base and height for triangles. The other main thing to remember is this: the area of a triangle is 1/2 base times height. So when I ask you for the derivative of the area of a triangle, we would get dA dt is equal to, let's just take that 1/2 out of here for a second. And how would we take the derivative of b times h? Well, you guessed it, that's going to be the product rule. So erase that. We will take the first function times the derivative of the second, so base times dh dt, plus the second function h times the derivative of the first, dB dt. Now, if you would like to distribute the 1/2, of course you may, but in this case here, I'm just going to leave the answer this way. Now, what about the perimeter formula for a triangle? Well, the first side on the bottom is technically called the base. These other two sides, well, you would have to be given information about that if you wanted to find the perimeter about this triangle. In most situations, you will not have to deal with that. So let's move on to the next shape. So now we are going to be dealing with our three-dimensional solids. For three-dimensional shapes, you're going to want to know volume formulas and surface area. Now, as we've talked about before in class, volume is about the stuff that is contained inside of these shapes, whereas surface area is the surrounding surface. Volume is also three-dimensional. Surface area is actually only two-dimensional. So let's start with our cylinder. For this shape right here, our volume formula is something we've talked about before. It is volume equals pi r squared, which is the area of the circle, but then times h. Now this is going to be a bit tricky. The derivative of volume with respect to time is going to be dv dt equals, now the pi, my suggestion is don't worry about it. Pull it out as a constant so that we don't have to worry about it for this next step. For the derivative of r squared times h, I'd like to challenge you with this. Pause here and take the derivative of r squared times h. You should know what rule to use, and once you're done, check back in with the video and see if you guys got it correct. Alright, well, welcome back. If you took this derivative using the product rule, you should have gotten this: r squared times dh dt plus h times, be careful, what's the derivative of r squared? That would be 2r dr dt. It's very common for people to miss the 2r here, but if you remember that r squared is a small function that you can simply take the derivative of, hopefully that won't cause any problems. Okay? Now, what about the surface area function of a cylinder? Well, again, this can be a little complicated, so give some more room here. For surface area, your formula will be as follows. There are two circular regions on the top and on the bottom that encompass your cylinder. But the piece that wraps around the two circles, when unraveled, is actually a rectangle. The height of the rectangle is h. The length of the rectangle, when you unravel it, is actually the circumference. So our surface area formula for this is actually going to be 2 pi RH. Now once again, this is a fairly complicated formula. You generally don't have to memorize this one, but if I did ask for the derivative of this function, or this formula, what would we get? Well, let's get dA dt on the left is equal to, and here we go folks, 2 pi r squared plus 2 pi RH. I'd like you to pause the video now and try to take that derivative as well. See if you can get the correct result for the derivative. Okay, and welcome back. Now, when you took the derivative, hopefully you saw this is actually two separate parts. The first part right here does not involve any weird rules for derivatives. It's simply just a derivative with respect to r. So we'll get 4 pi r times dr dt. Now, the next part definitely takes a little bit more thought when it comes to how to take that derivative. So if you notice, there is a 2 pi, which I want to leave out of there, and r times h. Yep, this is going to be another situation involving the product rule. So I'm going to take the first times the derivative of the second plus the second times the derivative of the first. So if you were dealing with a surface area situation and you needed that derivative, well, now you have it. Let's move on to cones, which will have much of the same ideas as what we had with the cylinder. First, let's start with volume. The volume of a cone is really similar to the volume of a cylinder. If you notice, I'm going to leave some space here for a reason. But if you do pi r squared h again, that would be the volume of an entire cylinder. Now if you notice, what's different about a cone versus a cylinder? Well, instead of having a circular base on top of this, a cone comes together to a vertex at the top point. That means a cone is actually smaller than a cylinder if you had all the same measurements. The question is, how much smaller is it? Well, there's a magic fraction that if you ever learned from geometry, it's actually exactly 1/3 the size of a cylinder. In other words, it would take 3 cones to fill up one cylinder in this case. Now, excuse me, as you guys know, we need to take the derivative with respect to time. So at this point, hopefully you guys are getting a good feel for this, and you would get dv dt equals, and really folks, it's all about not memorizing these derivatives, but just getting the hang of how you take a derivative even when you're dealing with a formula. So I'm going to get the 1/3 pi out of there, and what are we going to get inside here? Well, let's get the first function r squared times the derivative of the second, dh dt, plus the second function h. What is this going to be again? Times the derivative of r squared. That would be 2r dr dt. So there's our volume formula and the volume derivative. So now let's get to our surface area formula for a cone. And this one's going to be only one circle this time. And I know an ice cream cone doesn't have an actual circle covering it, but a true cone has that circle on the bottom that represents part of the surface. So there's the circle, plus, and in this case here, the surface area of the part that wraps around a cone is actually given by this, pi r L. Now what the heck is L in this situation? L is what we call the slant height, and it's represented by this distance right here on the edge of the cone. So if you were dealing with this situation and you had to take the derivative of this equation, again, this should be pretty straightforward now. dA dt equals 2 pi r dr dt plus pi times, and let's go ahead and use product rule, r dl dt plus L times dr dt. All right. So those two shapes, definitely a lot of stuff going on, but let's wrap up with two easier shapes, in fact. Let's get to our cube and our sphere. Now, just like how earlier squares and circles only had one variable, the beauty about cubes and spheres is it's the same idea, but now in 3 dimensions. So, with only one variable to deal with, these formulas are a bit easier to get. So, the derivative, the volume of a cube is simply length times width times height, but in this case, that is s cubed. The surface area of a cube is simply the 6 faces added up all together. So, if there's 6 identical faces, and they all have an area of s squared, well, there's our area formula for this. So what I'd like you to do is take the derivative of these two equations, these two formulas, and once you, pause the video now. Once you have the derivatives for these two, check back in and see if you guys got them correct. Again, these are not worth memorizing. To me, they're way better to just know how to solve yourself. Okay, see you in a bit. Okay, welcome back. So the derivative, hopefully for volume that you got, was dv dt equals 3s squared ds dt. And that's all you got to get. And then for surface area, we would have dA dt is equal to 12s ds dt. Hope that one went okay for you. So let's go over now to the sphere, and this one will be a very common one, so get used to this. This is a very, very common type of volume and surface area question. The volume formula for a sphere is going to involve, and leave some space here, pi, since it's circular, and it's going to involve r cubed because it has to be 3 dimensions. But once again, there's a weird fraction that goes with this. Perhaps you might remember from geometry, but perhaps not. This is the strangest one. It's 4/3 pi r cubed. Now the surface area formula is pretty amazing, and you'll see why in a moment. The surface area formula is 4 pi r squared. And again, notice it's r squared since it's an area, two-dimensional area we're finding. So what I'd like you to do, again, is take the derivative of each of these equations, find out what you get, and this time, before you pause, when you find the derivatives of these, you should come across something very bizarre. When that happens, spend a moment to think about it, then check back in with the video and see if it is the same thing that you thought of. Okay, welcome back. Hopefully you got this derivative here, dv dt is equal to, well, when the 3 comes down here, it actually will cancel out the 3 denominator. If you did this correctly, you should get 4 pi r squared dr dt. Now, did you notice something here? The derivative of volume is the same as the surface area equation. You guys, what does a derivative tell you about anything? It tells you the rate at which it's changing. Imagine a sphere, and if it were filling with air and it started to expand, if I asked you how fast is the volume changing at any moment, the amount that it expands is technically one tiny thin slice of the actual surface area of the sphere. Imagine a sphere going from a certain size to just barely a fraction of an inch bigger. If I asked how much it grew, you can almost imagine it being one layer of area that it's growing. So in that sense, the derivative of volume is surface area for this specific shape. Okay? Now, that's not something you have to memorize, but I just feel like that is something that helps people understand what a derivative actually is. So, the derivative of surface area, on the other hand, would give you dA dt equals 8 pi r dr dt. So, this wraps up the essential formulas and skills of knowing how to solve related rate problems involving all these geometric shapes. Okay? Make sure you know how to find the formulas for these shapes, but then more importantly, how you then take a derivative. For our first example, example A, we're going to be examining the sphere. Now, if you look at the notes we just took, you know that spheres have two potential formulas that could be used, either volume or surface area. So in order to figure out which ones we need, read the question. It says, the radius of a sphere is increasing at a specific rate, and then it says these words. At the instant when the volume of the sphere is increasing at a certain rate, they ask you what is the surface area of the sphere. So notice they use both, which means we're going to need both equations. Let's go ahead and write those in now, just so that we can use them when they actually come up. So volume, we know, is 4/3 pi r cubed, and we know that surface area is 4 pi r squared. Now what do we do with these formulas? Nothing yet. Let's make sure we read through this question correctly and get all the key pieces of information down. So unlike before with Pythagorean theorem, we don't need to actually go through and draw a picture of this, because all we have to do is find the important information and learn how to apply it into our two formulas. So it tells us the radius of a sphere is increasing at a constant rate of 2 centimeters per second. Now that sentence tells you so much information, but the key now is to understand this. What variable would you use to represent 2 centimeters per second? Well, it said radius, so we know we should use the letter r, but it says constant rate. So instead of saying r, what would be the rate variable for r? How about dr dt? Now the other keys to look at is, it says increasing at a rate of 2 centimeters per second. So when it says the word increasing, you know that we're actually going to get a positive 2 here, and this is going to be 2 centimeters per second. Now, if we continue reading, they tell you more information about the volume. They say that at the instant when the volume of the sphere is increasing at 32 pi cubic centimeters per second. So when you look at that, what variable would we use for the 32 pi? Well, it's about volume, which is v, but then it says increasing, and if you look at those units, that's one of those dead giveaways. This is talking about a rate at which the volume is increasing. So we're going to write dv dt equals 32 pi. Now finally, when we get to what the question is asking us for, it says, what is the surface area of the sphere? So do they ask for the rate or the actual surface area? In this case, they want the surface area. So I'm going to go ahead and say A equals question mark to designate that that's what we're going to try to solve for. So notice we don't have any diagram. We just went through the problem and wrote down all the main key information and tried to figure out what variables they represented. So since the question said, what is the surface area, and we've correctly identified where you need to solve for A, which one of these two formulas do we need to use? Well, it would make sense that we try to figure out the surface area, right? So our surface area is 4 pi r squared. So let's just go ahead and plug in the radius to get our answer. Is this the radius? No, that's the rate of the radius. This is definitely not the radius. You know what? This problem never told us. So what do? Just like in the last module, when you're doing a related rate problem, almost always something is missing. In this case, we need to figure out what the radius is. So what could we possibly do? Well, we have this formula that we haven't used yet, and we have this piece of information right here that says dv dt equals 32 pi. So what I'm wondering is, how do we turn v into dv dt? Well, hopefully you guys have figured out in this chapter, everything is going to revolve around taking a derivative. So what's the derivative of this equation? Well, we'll get dv dt equals 4 pi r squared, and then don't forget dr dt. Now take a look at the derivative we just took. How many variables do you see here in this equation? Hopefully you guys are identifying this now, but this is a variable. It's a rate variable. That's one. Here's another variable. That's the radius. And then here's a third variable, another rate variable. So if I were to correctly try to use this equation, notice how I'll set this up. For every unknown, I'm going to go ahead and just leave some parentheses so that we can fill in the information we've got. So let's start with dRdt equals 2. So that's going to go here in that space. Then let's get our volume rate, which is 32 pi, and that's for dV dt. So let's put that here. Now what are we going to plug in for the radius? Well, see, that's the one thing that we didn't know. So let's go ahead and just leave that in as an r, and let's solve for it. So we get 32 pi equals 4 pi r squared times 2. Scroll down a little bit, and we'll get 32 pi equals 8 pi r squared. Let's divide both sides by 8 pi, which is very convenient because now the pi's cancel out, the 8 pi's are gone, and we get 4 equals r squared. That must mean that r is equal to -2 or +2. Now in a geometry problem, -2 really doesn't make sense as an answer. What is a negative radius? It doesn't apply here. So let's go ahead and use r equals 2. So what are we going to do with that? Well, just think back to where we were a moment ago before we got stuck. We wanted to know the surface area of this sphere, and the only thing that we were missing was that radius. I believe we have it now, so let's plug in our 2. What is our surface area in this problem? Well, our surface area is 4 times pi, 2 squared is 4, so our answer would be 16 pi. Now, surface area units are always square units. So go ahead and scan that question. You'll notice the whole problem is talking about centimeters, so we will go ahead and go with square centimeters as our answer. And that's the first example. For our second example, we're going to look at example B, which is about cylinders. Now, anytime you're dealing with a three-dimensional shape, again, you got to read through the problem and find out. Are you going to be dealing with volume, surface area, or both? Now, when you read this question, it's very deceiving. They tell you a circular oil slick. They want you to believe this question is about a circle. But it says of uniform thickness. A circle with thickness is actually a cylinder. Now, it tells you that it contains 100 cubic centimeters of oil and that it's a very thin cylinder. So right away, this picture is going to be something that not only is hard to imagine, but it would be helpful if we actually draw it. Now, it tells you that as the oil spreads, the thickness decreases at a very small rate. And then they ask what rate is the radius of the slick increasing when the radius is 10. Your typical related rate question with a ton of information, and really our number one goal is to try to assign each of the pieces of info to a variable. So let's start by getting a good picture drawn for this so that we can get a good view of what we're dealing with. So a very thin cylinder. So this is the circular oil slick, but if it has a slight thickness to it, we're going to draw it like this. It's almost like it's like a disc with a very, very small height in this case. Now, what variables are we dealing with on any cylinder? Well, we're dealing with the radius, and we're going to be dealing with the height, which is that tiny distance right there of how thick the oil spill actually is. Now, the oil spill, you guys, in this problem, if you can imagine this, if there was an oil spill in the ocean, it would look like a circle. But if it has thickness, again, I want you to imagine this really, really thin cylinder. Now, as the oil spreads, what happens? Well, the thickness will slowly decrease, and the radius will slowly expand. So the whole point of this question is to figure out how is that relationship between the radius and the height changing as you read through this question. So now that we know that r is our radius and h is our thickness, let's read through this question and figure out what other information they tell us and assign things to our variables. So let's begin with the first clue. They tell you that the oil slick contains 100 cubic centimeters of oil. Now, what is 100 cubic centimeters, the radius or the height? Well, if they tell you cubic centimeters, we should know that that's actually telling us the volume of the cylinder. So in this case, that tells us we're going to be using volume in this problem. So volume is 100, and let's go ahead and just say V equals 100 for that. It's not the rate, it's simply the volume. Now let's keep going. The next major clue they tell us is that as the oil spreads, the thickness decreases at a rate of 0.01. That's a loaded sentence because they tell you everything. They tell you that it's the thickness, so we know we're dealing with H, but they say that it's the rate. And again, if you look at those units, centimeters per minute, this tells us it's not H we're dealing with, it's dH dt we want to know about. Now it tells you 0.01, but what's the key word here? It tells you that it's decreasing at a rate of 0.01. So that would be a negative 0.01. And that negative is so key to remember that every rate can either be a positive number or a negative number, depending on if it's increasing or decreasing. Now finally, they ask us to solve for the rate at which the radius of the slick is increasing. So what do they want us to solve for? They want to know the rate of the radius. So we're going to solve for dr dt. And they give you one last clue. They tell you that the instant that they care about is when the radius equals 10. So we can go ahead and fill in that in this case, even though we don't know dr dt, we know that the radius being 10 is really the variable r that we're going to be using. So let's put all this together, and if you notice, this problem never said anything about surface area. This is definitely a volume situation. So what is our volume equation for a cylinder? That would be pi r squared times h. Now, before you take a derivative, is there anything in this equation that stays constant? Well, we know the radius is growing. We know that the height is shrinking. But what about the volume? You know, they tell us that the volume is 100 cubic centimeters, but does that ever change in this question? Does it ever tell us that more oil is being spilled or that somehow it's being removed? No, the 100 cubic centimeters, this is actually a constant number. So if you wanted to take the derivative right now, be my guest. But on the left side, you would get dv dt, and you might get confused as to what to put there. And the answer technically would be 0. So instead of worrying about that, here's what I suggest. Fill in the constant right now. That way, when you take the derivative, you'll remember that a derivative of a constant is simply 0, and that means the entire left side of this equation will be very, very easy to write out. The derivative of 100 is simply going to be 0. So what's the derivative of the right-hand side? Well, from our essential formulas, you've done this already. I'm going to take the pi out here and do the first function times the derivative of the second plus the second function plus the second function times the derivative of the first. What's the derivative of r squared? That would be 2r dr dt. Now, in a related rate question, you got to remember that when you see this equation now, every single variable needs to be accounted for. So when we write this out, before we get started with plugging in our numbers, I just want to leave some room for everything. So we have r squared times dh dt plus h times 2 times r times dr dt. This is a really good habit to get into simply because it helps you organize all the information that you're really dealing with. So let's take a look at the numbers that we already have, and let's see what we can fill in. So our volume is 100. Our dH dt is negative 0.01. We're solving for dr dt, and the radius is equal to 10. If I remember all that correctly, let's fill in all the information that we've got. So the radius is 10. Let's start with that. Radius shows up here and here. So conveniently, I can put a 10 for radius and the 10 for radius in two places. dH dt, our negative 0.01, will be taken care of here in this variable. So negative 0.01. And then we're solving for dr dt, which, if you notice, shows up here at the tail end. So I'll go ahead and just write dr dt, since that's what we're going to solve for. Now, interestingly enough, once again, if you've caught the theme now, there is something missing. And I swear we looked at everything that we had from the problem and filled it all in. So what is this missing value? Well, if you look right here, it's h, and they never told us what that is. So how do you deal with that? What are you going to do when there's a piece of information missing? Well, the point of related rates is to make you really think carefully about all the information you have so far. Now, since they gave us the volume, let me slide this over. The volume equation was pi r squared h. Now, I believe they told us the volume was 100. And if you think about it, if we need to figure out what h is, let's use the equation that actually gives us an answer for h. But what would you plug in for the radius? Well, believe it or not, they told us that. They gave us the 10, which means we can solve this problem right now for h. So whenever you're missing information, think about what variable it is that you don't have, and use any information you can to come up with what that variable is. In this case, we're missing height, so let's use the volume equation, since it has height involved. So through this process, we'll get 100 equals 100 pi times h, and then solving for h gives us 100 over 100 pi, or in other words, h is equal to 1 over pi. So that should be helpful now because we can have something to use for our h. So let me go ahead and plug in 1 over pi here. So in the end, this problem just comes down to calculating all of this. So what do we end up getting? Well, let's just take things one step at a time. In order to solve this problem for dr dt, let's see if we can simplify some of this to make our lives a little bit easier. So pi times 100 times negative 0.01 plus, well, if you combine those three numbers there, we'll get 20 over pi dr dt. So 0 is equal to pi times 100 times negative 0.01 is going to give us negative 1 plus 20 pi dr dt. And at this point now, if you want to distribute the pi, go ahead. We can get negative pi plus, the pi's conveniently cancel here, giving us finally pi on the left equals 20 dr dt. And so from there, dr dt is going to be equal to pi over 20. Now, what does dr dt mean? That's the rate at which radius is changing. Now, we knew that the radius was slowly expanding, so did we get a positive answer? Pi over 20 certainly is positive. What about our units? Well, since this is a rate, let's take a look at that problem again. And if you notice, everything in this question is given in terms of centimeters and minutes. So what will our units be? For dr dt, we should specify centimeters per minute. So here is our final answer, and that concludes module number 2. Have fun.